Hello, pre-calc honors students. Here we are with vectors in 3 dimensions, and our objective is to extend vectors to 3 dimensions and to apply them. We see that many of the same vector rules still apply in 3D as in 2D. But how do we set it up? A 3D system, because we're so used to a 2-dimensional system. Well, let's let Willy Wonka's Oompa Loompas help us out here. Here's an Oompa Loompa standing here with his hands on the XY axis on the blackboard, and he rotates and creates a third axis through his head. I'll demonstrate this in class. And you could just think of taking our old XY axis and putting another axis in there. But notice how the X-axis is the one that comes towards you, the Y-axis, the horizontal one, and Z is the vertical one now. In this paper, I'm going to have plenty of extra sheets of this for you to practice with. How do we plot a point 2, 3, 4? Well, there's a couple ways to do this. Let's start with a box. For the point 2, 3, 4, we can think of going in each direction first. Let's just back up. Do you remember how you would plot something on standard axes, like 2, 3? Sure. 2, 3. You'd start off going 2 in the x direction. You go along the x-axis, go 2, and then 3 in the y. And there's your 2, 3 point. Now, could you have gone up 3 first and then over 2 on the y? Sure. In some ways, that's another way to look at it. But let's look at it that way. We'll just do each dimension as a little vector and end up adding them up. 2 in the x direction, so 1, 2 in the x. There's our 2 in the x direction. 3 in the y. From where we left off, 3 in the y. Gets us over to here. So that's actually the vector 2, 0, 0. And this is the vector, this gets us to the point 2, 3, 0. And now we go up 4 in the x direction, or 4 in the z direction, which is about that long. So we're going to appear like this. And there's 2, 3, 4. So a resultant then is the thing that connects those two. Let's put that in this vector that starts at the origin, goes up to there. That's our resulting vector. We can also think as the point. So, if you followed along with the arrows, I did it that way. Another way to do it is make a box. 2, 3, 4 with a box technique. The box technique sort of corresponds to what you may have done before, where we could have also gone up 3 and over 2 and looked at this rectangle in 2 dimensions. That 2, 3 is the opposite corner of a rectangle from the origin 0, 0. So we're going to view that the same way now with the box. So I want you to compare and contrast these two, so let's split the screen. We make a box that's 2 in the x direction, 3 in the y direction, and 4 in the z direction. And now we come up with the other corners of that box. Well, first of all, here's a rectangle in the YZ plane. Here's a rectangle in the XY plane. Here's a rectangle in the XZ plane. And now we can draw lines parallel to the sides we have drawn to finish our box. Do you like the box there? And again, we get the same vector. Coming up from here like that. Boom. And here again is the point 2, 3, 4. We can also think of it as the vector 2, 3, 4 that takes you from the origin to the point 2, 3, 4. Okay? Now, what are the equations for all these planes? The XZ plane. All these points are like this. This is 3, 0, 2. And this is 0, 0, 6. 0, 0, 6. Let's get one more. Maybe we'll see a pattern here. Let's do 1, 0, 4. What do these all have in common? A y coordinate of 0. So the XZ plane is y equals 0. the xy plane, z equals 0, and the yz plane, x equals 0. So for the x-axis itself, we used to have an easy formula, which was just y equals 0. But y equals 0 now is the whole xz plane. So you got to put these two ideas together. The x-axis then is y equals 0 and z equals 0. If you intersect these two, the xz plane and the xy plane, here's the xy plane, here's the xz plane, they cross in the x-axis. So for the y-axis, we actually have to create a line here by defining it as the intersection of the xy plane and the yz plane. So that's x equals 0 and z equals 0. And for the z-axis, x equals 0 and y equals 0. And you notice that's the point right here. 0, 0, 6 has both its x and its y coordinates equals 0. It's on the z-axis. We also have octants. And right now you're just seeing the first octant, where x, y, and z are all positive. But you could certainly have x, y, and z all negative, and that would be a different octant. I'm not going to get into numbering the octants right now. Just trust me, there's 8 of them. Because each of the 3 variables, x, y, and z, can be either positive or negative. So instead of 4 quadrants, 8 octants. Now, what does that do with our formulas then? Let's come up with the distance and midpoint formulas between points. So if you have 2 points, A and B, so if you put A anywhere in here, make a big dot for A. Now, it's hard to actually get the bearing on where A is, because they don't have any of the reference points around it. And if I put a point B over here like this, here's A and here's B. But what I can do is set up a little box like this to give you the impression that B is in the opposite corner of that box. There you go. And going from A, which is x1, y1, z1, to B, which is x2, y2, z2, can be tricky. But basically, we can get the distance by doing the Pythagorean theorem a couple of times here. This gap in here is the absolute value of x1 minus x2. I'm sorry, this is the change in y's. So technically that's actually y1 minus y2. And this gap in here would be x1 minus x2, absolute value times. And this change in height then would be z1 minus z2. And so you can figure out from the Pythagorean theorem the distance along the base here. And then you've got to plug it in again. So let's find out just this distance. We'll call that d for right now. D is the square root of x1 minus x2 squared plus y1 minus y2 squared. You're familiar with that distance formula. But now when I want to get this other distance, that comes up here like this, I have to finish my triangle like this. Now this difference in z's is perpendicular to this xy parallel plane here. So now to find, we'll call this big D. Big D is going to be the square root of little d squared plus z1 minus z2 squared. And I think when you put this into here and that gets squared, you come up with a big square root. The square root of just the difference in all the components. x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. Notice we don't need the absolute values because we're squaring those differences. And the midpoint can be halfway in between there. We can do the same extension what we did before, and that's just average all the coordinates. x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. Okay? There's your distance and midpoint formulas, given the 2 points in 3 space. So a sphere has points A at 8, -2, 3, and B, 4, 0, 7 as endpoints of its diameter. Find the center C and the radius R. This could be a little too hard to actually draw a picture of, but let's give it a try. We're at 8, -2, 3, 1, 2, 3, 4, 5, 6, 7, 8, -2, 3. See, I'm starting to go off the paper anyway. We'll use that for something else later. The center is easy because the center equals the midpoint of line segment AB. So we can do the average of the x's, 8 plus 4 over 2, the average of the y's, -2 plus 0 over 2, and the average of the z's, 3 plus 7 over 2. And you end up with 6, -1, 5. That's your center. And now a sphere is a set of all points equidistant from the center. So let's figure out the distance. Yeah, let's just take this thing out. A sphere is a set of all points equidistant from a central point. We've got that central point. Now let's figure out what the radius has got to equal. The radius will equal the distance from the center to a point. So let's go from C, 6, -1, 5, to 4, 0, 7. So that distance equals the square root of 6 minus 4 squared, plus -1 minus 0 squared, plus 5 minus 7 squared. Square root of 2 squared is 4, -1 squared is 1, -2 squared is 4, the square root of 9, which is 3. So for our circle then, so for our sphere, it's much like the equation of the circle, we just add in the third component. X minus x, x minus the center. Oopsie, eraser. X minus the center, which was 6, 6 squared plus y minus a minus 1 squared plus z minus 5 squared equals r squared, 3 squared. So you get x minus 6 squared plus y plus 1 squared plus z minus 5 squared equals 9. I suppose you could expand it out. And then, if someone would give you the expanded out form to find the center and radius of the circle, you'd have to complete the square in all 3 variables. Oh, that would be fun. And that's the equation of the sphere. I just did already too. We found the center and now we got the equation. So, the equation of a sphere with center x naught, y naught, z naught, and radius r is going to be x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. Now, the line containing x naught, y naught, z naught with direction vector ABC is just an extension of what we did with lines before. X, y, z, 3 coordinates for the point, is equal to the point on the line x naught, y naught, z naught, plus some parametric variable t times the direction vector ABC. There you go. So find vector and parametric equations for this line containing A, which is 2, 3, 1, and B, 5, 4, 6. This time, let's try and just do a quick picture here. 2, 3, 1. That's our point A. 2, 3, 1. And B is at 5, 1, 2, 3, 4, 5, 4, 1, 2, 3, 4, 6. 6 is about the whole height of that thing, so it's up here. So here's B at, let's do this in blue, 5, 4, and then up 6. Let's see, like that. 5, 4, 6. There's point B. And so we're trying to come up with a line that goes through those. Something like that. Now it's very hard to see and get a grasp on this in 3 dimensions. But there you have it. There's the line going through those 2 points in 3 space. The diagram will not be necessary on doing these things. I just wanted to give you an idea. So first we need a direction vector from A to B. So AB, that vector, will equal B, 5, 4, 6, minus A, 2, 3, 1. That's how you go from A to B. You got to subtract them in that direction. So you get 3, 1, 5. That's your direction vector. And now you can use either point. So for x, y, z, for now your vector equation of the line, you get either point, let's take 2, 3, 1, plus t times 3, 1, 5. There's the vector equation of the line. Now I think we're also supposed to come up with parametric equations too. So let's sneak that one in too. That's the vector equation. And here's the parametric equation. We just separate out the things here. We continue our x, y, z equals 2, 3, 1, plus we can distribute the t. It's a scalar multiplier, so 3t, 1t, 5t. And so x, y, z equals 2 plus 3t, 3 plus t, and 1 plus 5t. And now you can set all the components equal. X equals 2 plus 3t, y equals 3 plus t, and z equals 1 plus 5t. There you go. Now, trying to get this all into one equation, x, y, z, is not going to work out so well. Because when we just get linear equations x, y, and z, we're going to see it's a different shape. It's not a line anymore. But that's another chapter. Now, basic vector properties. If you've got two vectors, then we have the following properties that happen here. Vector addition, u plus v, u plus v, it's just going to be adding up the corresponding parts. x1 plus x2, y1 plus y2, z1 plus z2. Scalar multiplication, k times some vector u, is k times x1, y1, z1, and you sort of distribute that k scalar multiple. K times x1 plus, oh, not plus, kx1, ky1, kz1. The magnitude of u comes from the distance formula we talked about before. That will be the square root of, and this is vector u, x1 squared plus y1 squared plus z1 squared. Dot product of uv dotted with v, again multiply the corresponding parts. So it becomes x1 x2 plus y1 times y2 plus z1 times z2, and again you get a scalar. And finally, the angle between two vectors. We're going to need a big page for this. This is number 5. The angle between two vectors, we can use our cosine theta again, and we can still get by with u dot v over the magnitude of u times the magnitude of v. Same principle applies from what we saw before. So example 3, find a vector equation of the line through 1, 5, negative 2, parallel to the line with equation x, y, z equals 8, 0, 1 plus t times 4, 3, 2. Well, from our line L, this is the direction vector. So we don't actually talk about a slope. It's very hard to talk about a slope of a line in 3 space because you have it pitched to all 3 different planes or in all 3 different axes. So we talk about a direction vector of the line. So if we keep the same direction vector, we'll create a parallel line to L. Okay? But we have to want to go through this point. So there's your point, 1, 5, negative 2. So our new line is just going to be x, y, z equals the point 1, 5, negative 2 plus t times the direction vector 4, 3, 2. Now technically what we could do is you could use a new variable for t there. it's not absolutely necessary. But sometimes you find that if you want to see where two lines intersect, you're going to have to do that and set up two variables that way. Now, example 4, find the measure of angle theta, the angle between vectors 4, negative 5, 3, and 7, 0, negative 1. So we can just go through the work here of cosine of theta should equal the dot product of these two vectors, 4, negative 5, 3, dotted with 7, 0, negative 1, all over the product of their magnitudes. So that's the square root of 4 squared plus negative 5 squared plus 3 squared times the square root of 7 squared plus 0 squared plus negative 1 squared. And so you get the cosine of theta is 28 plus 0 plus negative 3 all over the square root of 16 and 25 and 9 times the square root of 49 and 1. So we're getting cosine theta equals 25 over the square root of 50, I believe, yep, times the square root of 50, which is conveniently 50. And so we get the cosine theta equals a half, and so that happens at 60 degrees. So our special angles. That's the angle between those two vectors in 3 space. Okay, flange out.